Now, to simplify some of the computations and calculations in mechanical system or even in electrical system, we we tend to use this analogy between the two systems, the electrical translational system and the electrical or the mechanical translational system and the electrical system. Now, when we do that, the concepts or the laws in electrical theory, we can apply them now to solve problems that involves mechanical translational system. This is the same true as the rotational mechanical system, because the only difference between the two is we just change the force with torque, we change the displacement with the angular displacement, and all throughout they are all the same. It has also a damper and also a spring in the different system. So we can just look at the relationship between the translational mechanical and the electrical system. So first, there are two types of analogy that we will be looking at. The first one is this. This is the series analogy, or they also call it the force voltage analogy. So force voltage means the force in translational mechanical system is equivalent to the voltage in the electrical circuit. So if we remember in mechanical translational system, mechanical translational system, if we look at the different components, we have a mast, we have mast M, then we have also the spring with a spring constant Ks, and we have the damper with the constant Kd. And usually our input here is we can apply a force F of t, then our output is usually the displacement x of t. In electrical system, this is equivalent to RLC. So we have a voltage E, is our input. Then we have the components are R, L, and C, the capacitor or capacitance C. And here we have our current I's of T. And now if we want to determine the analogy between two, so remember forced is equivalent to the voltage here. How about the other components? How about the current in the electrical system? What's the equivalent of the current in the mechanical system? To determine the equivalent, we can look at them individually. So if we have, let's say, first the spring or the damper. Let's just look at the damper first. So if we have only the damper, then we have a mass here, M. Then if we apply force F of t, or just let us just look look at the mass first. Only the mass. If we have only the mass here, so from our equation, in terms of the force, the F of t will be just equal to the force due to mass, and that was equal to the mass times the acceleration, or x double dot x of t. Because this is the summation of all the forces, and the only force that exists here will be the input F of t, and it's equal to mx double dot t. In the voltage, so here in the voltage, if I rewrite this, we don't have any in RLC circuit. We don't have second derivative component voltages along RL and C. So we can just rewrite this into first order derivative. by converting this double dot t into a speed or velocity. So this will be just equal to m, the derivative of the speed, because this is the acceleration with respect to time, m dv dt, where v here is the velocity. And here in the RLC system, where can we find this similar equation with a derivative multiplied a constant? Remember, f of t is a voltage, so the voltage drop across these three. Where is this similar term here? So for the resistance, the voltage drop here is this I times R, so it cannot be this in this form. For L, the voltage across the inductor, we know that that is the voltage across an inductor. So if we apply a voltage on an inductor L, then we have a current I. Then this is E of t, and we have I of t. If this is L, we know that the voltage across there, V of L, or just V, or just E. We can just use E here. E of t will be just equal to L times di dt times the derivative of I here with respect to time. And if you look at that, the force, the voltage, and derivative, a constant, and a constant. So from here, what's the equivalent? We can observe that mass now, M, in electrical circuit is equivalent to L, inductance. And we can also say that the velocity here, V, velocity, is also equivalent to what? To the current in electrical system. So we derive the analogy. Mass is equivalent to inductance, velocity is equivalent to current, and the voltage is equivalent to the force. Now, how about the others? So if we look at, so let's say the spring, let's look at the spring. So if we have a spring here, then if I apply a force F of t, and it's a massless spring, so this will be Ks. Now, what will be that F of t? So F of t will be just equal to the force due to the spring, and that is just equal to K as K of S times the displacement X of t. But again, this one, X of t, because our current here, we already said that I is equivalent to the velocity. So we need to convert this X here in terms of velocity so that we can find the equivalent of this in the electrical system in terms of current. So how do we do that? How do we take this X in terms of velocity? So we know that dv dt, or V, the velocity, the velocity is just equal to the change in the displacement with respect to time. So if I solve for x, dx will be equal to v dt. So x is just the integral of v dt. So we can replace that equation here. Instead of using x of t, we can just make it ks times the here x, which is the integral of v dt. Then in electrical system, what is this equivalent? The term, the voltage that has integral, we know that that's the capacitance. So if you draw the circuit, a pure capacitive circuit, and the voltage E here, then what will be the current I? If this is C, so the voltage is of T will be equal to the voltage across a capacitor. It's equal to 1 over C, the integral of I dt. But again, I is equivalent to V. Then therefore, K's of S and 1 over C are also equivalent. Or the other way around, the capacitance is 1 over K S. That's the relationship between the two. And lastly, for the damper, so if we have a pure damper, what will be the equivalent of this in electrical system? F of t, then we have a displacement x of t, and we know that that force due to damping is just equal to what? This is equal to the velocity times the damping coefficient. So this is as kd times the velocity, and it's already in the velocity, so we can just directly determine the equivalent of this here. And the last one here will be the resistance or resistor. And we know that the voltage across a resistor is of T is equal to I times R. So therefore, KD is equivalent to R. So KD is equivalent to R. So let's summarize this analogy. So for a force voltage, so in mechanical system, so force voltage, so number one, the mass M. This is equivalent to, mass M is equivalent to the inductance L. Inductance. So this is L. Or we can just start first for the we can include the force and the voltage first here instead of start with that one. So the force F is equivalent to the voltage E. Then for the current, this is equivalent to the velocity. So the velocity V is equivalent to the current I. Then for the other components, we have the mass. So number 3, the mass M is equivalent to, so this is current. Mass is equivalent to here the inductance L. Inductance L. Then for the spring constant, where's the spring constant? Somewhere here. This the spring constant K, case of S, constant, case of S is equivalent to, this is equivalent to 1 over C, the inverse of the capacitance, and that is called the elastance. Elastance. This is the inverse of the capacitance. This is 1 over C. Then lastly, for the damping or the damper constant, damping constant, KD. This is equivalent to, where's that KD? KD is equivalent to the resistance R. Resistance R. So now that we know the equivalence analogy between the two systems, so these are the analogies, we can now apply them in solving some problems. But before we do that, we need to take note some definitions or some of the analogies, definition of the analogies. So if in current, in electrical system, current in a series system, series circuit, the current through the components of a series circuit are all the same because they are in series. The same true in a mechanical system because they are now analogous. Therefore, the velocity also, if the components are in series, the velocities are the same. And also, The number of meshes in the circuit, the number of loops or mesh in a circuit depends on the number of mass in a mechanical system. So let me write that. So the first one, velocity in series. Velocity is the same in series. In series. Then we have the number of meshes, the number of mesh or loops in a circuit or loops is equal to the number of masses in mechanical system. And also the elements that connects two mass, elements connecting two masses is in electrical system. This is an common element in electrical. It is a common element, and we will illustrate that in our example here. So example, so if we have a translational mechanical system, a two mast, let's say this is 5 kilograms, then I have another mast here, let's say 10 kilograms, and they're connected with a spring with a damper. So maybe it's a shock absorber or something. Then this one is it has a damper here, a roller or a friction at the bottom. We can just I can just write here a damper, draw a damper. Then we have still a spring here that is connected to that 5 kilogram, and the same at the other side. So let's call this one KS1, this one KD1, or let's just put numbers here. So for the spring constant, usually the unit for the spring constant is Newton per second, or Newton per meter. Newton per meter. Because if you multiply that with the the force times the displacement, it will cancel out. The meter will cancel out and become force. So Newton per meter. For the damping or the damper constant, because this is force is equal to the velocity times the kd. So if I multiply the velocity with, it should be 1, let's say 1 Newton second per meter. So if I multiply this with the velocity meters per second, so it will be equivalent to 1 Newton. Then here, let's say this is 1.5 Newton per meter, and this is 1.5 also Newton second per meter. Then let's make this 1 again, Newton per meter, and 1 again, Newton second per meter. Now, if we have an input f of t here at 5 kilogram, so if I apply an input here, call it f of t, and the result will be a displacement of this one. Just call it x1 because this is due to this 5 kilogram, and there is also a displacement here for the 10 kilogram. Let's call it x2. Now I want to determine the transfer function if my output is this x of 2 and my input is f of t. So f of t is the input, while the output that I want is x of 2. What will be the transfer function of this system? Now, using the analogy, we will convert this, we will draw the circuit equivalent of this one. Then we will apply the laws and theorems in circuit to determine the transfer function. So take note of the analogies. So first, let us look at this part. This is just simple, like this our here in our example. So we have a source, so solution. So we start with the source, our source voltage now. This is equivalent to that f of t here. That is our input, f of t at mass 5 kilograms. So f of t. So this is f of t. Then at f of t, what are the components here? We have the spring, the mass, and the damper. So for the mass is equivalent to inductance. So we have an inductor here connected to the input. And the value for the inductance should be equal to the mass, M. And that is 5 kilogram. So let's just write this one as 5. Then next, we have two components here, the spring and the damping. So the spring is equivalent to the elastance, so the capacitor 1 over C. Then the damping is equivalent to R. So we have a capacitor and we have a resistor. So this capacitance here is just equal to 1 over C. So 1 over C is equivalent to 1. So 1, our Ks is just equal to 1. So 1 over 1 is just 1. And for the resistance, this is also equal to 1. Then, from the third definition here, because these are two masses connected to each other, then it says here that the components that connects these two masses is considered as a common component. So this should be, why is it common? Should be common component of the electrical system, or this is what it looks like. So this will be a inductor and or a resistor and a capacitor. A resistor and a capacitor. It's a common component between the two elements, the two masses. And this R here is just equal to 1.5, and this is also 1.5. Then we have another mass that is connected to this common component. So we just draw here that another mass, and that is 10 kilogram. And we have another two components. We have the resistor and the capacitor, and we have a resistor. Then we'll go back to that one. So this will be 1 and another 1. Then here, the current that flowing through here in this mesh loop is in the 5 kilogram. Remember that the current is equivalent to the velocity. So there's a current, mesh current here. Mesh current. And that mesh current is what? Is equivalent to the velocity. But this will be V velocity 1, because this is in the first mass, 5 kilogram. And here, we also have another velocity at the 10 kilogram. And there's a correction somewhere here. This 1.5 here, the resistance, the 1 over C, the spring constant. The spring constant 1.5, that should be equal to 1 over 1.5. It should be 1 over 1.5. Or it should be the capacitor, not the resistor. The resistor is equivalent to the damping, and the capacitor elastance 1 over C is equivalent to the spring constant. So this will be 1 over 5 here. 1 over 1.5. Or we can just make this as 2 to simplify our solution, our calculation. You can just make this also 2 or 3. And is 3, so that it will be exactly 3 over 2. So this will be 3. Or we can just use 4. So that 4 over 2 is 2. This will be just 2. And what else? And I also want to change my output here because I put my output to be the displacement. So instead of the displacement, why not just use the velocity so that I will not convert this one anymore in terms of the displacement. But if you want the displacement, it's just the same. You just need to take the integral of this velocity here. That will be the displacement. You just need to change them in terms of displacement. So now, let's try to solve our transfer function. Remember, our output is V2. Our input is f of t. So what will be the relationship between the two? Using our circuit analogy, we can just apply the Maxwell's method. So this is loop A, this is loop B. So we will have two equations. Then we will solve for b's of t in terms of f of t. So at loop A, so let's solve at loop A, applying KVL at loop A. Loop A, so we start at f of t. So this will be plus and minus f of t minus the voltage drop across the inductor. So what's the voltage drop across the inductor? This will be L di dt. But because our I is V, remember V1 is our I here, I1. So it will be, instead of I1, we use L dV1 dt. So this will be L, that is 5. Our L equivalent is 5. Then dV1 dt. Then minus across the capacitor, that will be 1 over C, the integral of I dt. So 1 over C is 1. Just remove that 1. And this will be the integral of I dt, or just V1 dt. And for the resistor, minus that is equal to the current times the resistance, I times R. Our current is V, so this is just V1. Then we still have a current here. It's not just the IA or V1 or the loop current B1. We have another loop current in the opposite direction. So if this is minus for the opposite direction, we can add that loop current. But before that, we solve for the loop current V1. So this will be minus 3. That's the resistance times V1, our current, loop current 1. Then minus 1 over C, or 1 half, the integral of I dt V1 dt. This is V1 dt. Then here we still include that V2, but in the opposite direction. So it will be plus V2 times 3. So 3 V2, then plus 1 over 2, the integral of V2 dt, or the capacitor. And this should be equal to 0. Then we can now take the Laplace of this to simplify our equation. So this will be f of s minus 5s v1 minus v1 over s minus v1 minus 3v1 minus v1 all over 2s plus here 3v2. then plus 1 over 2 or V2 all over 2S. And this should be equal to 0. So we have V1 and we have V2 here. We have three unknowns here. And we can simplify this further. F of S, we can factor out this V1. We have so many V1 here. This will be equivalent to negative 4 V1. Then 1 over S and minus 1 over 2S. Then we have this one minus 5S. So if we factor out now that Vs minus V1, then we have here 5S. Then we have plus 4 here. This one, then we can add this 1 over S plus 1 over 2S. That will be 2 plus 1 is 3. So this will be 3 over 2S. So these are all the V1s. And for V2s, here we have plus. We can also add them. 2 over S. 2 over S divided by 1 times 3. The 6S plus 1. And this is V2 equals 0. Then we can call this one our equation 1. Then for equation 2 at loop B. For loop B here, so we don't have any source voltage, so we can apply the KVL. So we have minus V2 and all the impedances along this loop. So minus 2, 3, 10, 1, and 1. So we have 10, or we can directly apply. Another way is, instead of writing this integral here, we can directly convert them first into the S domain before we apply the Kirchhoff's law. For the inductance here, then this is our L. The voltage across here, the voltage across this one. So you can do this. The voltage across this is L di dt. And L is 10, so 10 di dt. What's the Laplace of 10 di dt? It's just 10s. For the capacitance, this is integral of 1 over C. And that's just 1. So this will be 1 over S. Then for the resistor here, that is just equal to the voltage itself, V. And for here, this is also equivalent to 2 over, or 1 over 2S. 1 over 2S, that's the impedance here. If you remember, S is equal to J omega, or S is equal to zeta plus J omega. If you remove this zeta here, it's just J omega, and we know that J omega, or omega, is equal to 2 pi f. So in circuits, 2 pi f times XL, or C, or L, the inductance, this is equivalent to XL. So what we are doing is this: we are solving for the equivalent impedance of them when we're converting them into the S domain. So it's like this one, 1 over 2S. That's just the XC, because XC is 1 over 2 pi f times the capacitance. So your capacitance here is 2. Your S is 2 pi f, so 1 over 2S. For the resistance, this is equal to 3. 1 and 1. It doesn't change. Then we can now apply our law, Kirchhoff's law here, by just multiplying these impedances with V2, and we just multiply it with in S domain. Because we factor out V2 in S domain now, so we have 10S. We have 10S plus 10S then plus 1 over s, plus 1 over s, then we have here 1 plus 1, and for this part we have plus 1 over 2s plus 1 over 2s, then we have lastly for the resistance R 3. Then because this is a common element, there's another loop current flowing through this one, so we need to add that one, so plus here, so we have plus, and that loop current is V1. Then what's the reactances or the impedances here will be 3 plus 1 over 2s, 1 over 2s, and this should be equal to 0. Then we can solve for V1 here, because take note, so this will be our equation 2. We solve for V1 at loop B here, then we substitute that in this equation, then finally we will be having a transfer function or an equation that is in terms of f of s and just V2. So V1 now will be equal to this whole thing here will become positive. Let's copy this one. Then I divide this with this one, 3 plus 2s. Or I can just first simplify that numerator. Here we have 1 plus 3, that's just equal to 4. Then we have 10s. Then we have this 2, that's just equal to 3 over 2s. Then if you add them all, so this will be equal to 2s, 2s divided by, or times 4, that will be 8s. Then plus 2s times 10, 2 times 10 is 20, s squared, and we have plus 3. And at the denominator here, we can also add that 2s, then we have 6s plus 1. Then we can cancel out that 2s here. So V1 now is equal to, rearrange this, this will be 2s squared plus 8s plus 3 all over 6s plus 1. So this is now our V1, and we will substitute this in this equation. So I'll just copy this. But before we do that, we can simplify this first, just like what we did here. Or so this will be f of s minus b1, which is equal to this one. But before we do that, we simplify this one first. This is 2s times 5s, that will be 10s squared, plus 4 times 2 is 8s, then plus 3. Then you multiply it with v1, which is equal to this one. So 20s squared plus 8s plus 3 all over 6s plus 1. Then we multiply it again with v2. So this should be v2 plus s plus 1 over 2s times v2, and this is equal to 0. So if you look at our equation now, this is now in terms of f of s and v2 only. So v2s of s. Then solving for the output over input, the transfer function. So f of s will be equal to this whole thing. We can factor out that v's of 2. Paste it here. This one will become positive times. Then this whole thing plus or minus. There should be my minus, because I'll put this one on the other side. So s plus 1 all over 2s. Then all of them multiplied by b's of 2. but our output is v sub 2, our input is f of s, so v sub 2 all over f now will be equal to 1 over this whole thing. 1 all over this one. So I can just write it as 10s squared plus 8s plus 3. Then you multiply this with 20s squared plus 8s plus 3 all over 2s times 6s. So that will be 2 times 6 is 12s squared. Then 2s plus 1 times 1 plus 2s. Then minus s plus 1 all over 2s. This is now the transfer function of that system. We solve it through electrical way in solving the mechanical system. So this is the use of this analogy. So if you're more familiar with the rules or laws in electrical systems, so you can do that. You can just solve for the analogies, and after that you apply the theorems and laws in the electrical system. And you can also do the other way around. So if you are given an electrical system that you cannot solve, you can always convert them into mechanical system and look at it. If you're more knowledgeable with the mechanical system, then you can solve that